In this part, we're going to introduce some MATLAB code that can help us to do some analysis. So there will be 4 questions. The first one is we try to do spectral analysis for 2 voice signals. The first one is a female speech.
为什么要进行频域分析？
The second one is a male speech.
为什么要进行频域分析？
And before we do MATLAB coding, there is an introduction for how we need to do to convert a signal from time domain to its spectrum in the frequency domain. We generally use fast Fourier transform, FFT, to do that. There are 2 ways to call the FFT function. If without the parameter n, then by default, we're going to do a n-point fast Fourier transform. In case that the length is given by n over there, then the function will be forced to do n-point fast Fourier transform. And here are 2 cases between depends on the relationship between m and n. So in general, we ignore the parameter n here using the default behavior of the fast Fourier transform in MATLAB. And there's another oftenly used function, FFT shift. So the function is trying to move the DC components to the center of the signal. And in general, a signal spectrum is a complex function. So we generally have 2 parts. One is the amplitude spectrum, another one is phase spectrum. And these 2 functions can help us get the amplitude and the phase spectrum. Okay, let's get back to the first question. We're trying to analyze a female and a male voice signals. And here is the snippet. How can we analyze it? I'm not going through the details, but here we see we have to do a Fourier transform, and the results need to be shifted so that the DC components will be moved to the center of the view. And here are the way to plot it. And here is the spectrum for the first, the speech signal for a female. And this is the spectrum for the male speech. So it's clear that the higher frequency component is very rich in the female speech, but lacking in the male speech signal. The second question is, we're trying to compare a numerical spectrum versus its theoretical spectrum for a given signal. So this is a unilateral decaying exponential signal. We know that the spectrum is 1 over j omega plus 1. And here is the amplitude spectrum. Now let's look at the energy of the signal. Based on the Parseval law, we can calculate the spectrum using either format. And the result is 1 over 2. Quite straightforward. What if we have only a band-limited signal? So the integral, the lower and the upper limits is limited to omega sub m, is maximum angular frequency. So based on the Parseval law, we can calculate the energy if the signal is forced to a certain range of frequency components. Now, let's see, if we try to sample the original signal using sampling frequency equal to 8 Hz, then to avoid aliasing, the maximum frequency has to be not greater than 4 Hz based on the Nyquist rate, so that the energy will be forced to 2 pi times f sub m. So in that case, the energy is equal to 0.4873. and it's only 97% of the original signal's energy. And what if we increase the sampling rate? Then this percentage will be improved. So that if we're trying to sample the original signal using a certain sampling frequency, then the energy or the signal will have to be distorted a little bit. And here is the snippet to calculate the theoretical and the real signal. And here are the plots. The theoretical spectrum is given as the red dots, while the blue lines represent the approximation if the signal is sampled by this sampling frequency. And here is the other case. If we sample the signal using the frequency equal to 16 Hertz. And you can see there's some discrepancy between the theoretical spectrum and the real spectrum if we have the limited bandwidth due to the sampling in here. The next example is we're trying to compare the spectra between a real-life signal and an ideal signal. So we're trying to sample or trying to analyze a cosine signal. It's very straightforward, cosine of 100 pi t. We know that this is the spectrum for the cosine signal. That is the graphic representation in the frequency domain for this signal. However, in reality, we cannot have a cosine signal because it will last to infinitely long time. So we'll have to do a truncation in the reality. So whatever cosine function we encounter in the reality must be a truncated cosine function. Based on the modulation theory, we understand that the spectrum is supposed to be this function. And here is the representation in the frequency domain. Now, if we try to use MATLAB to do the analysis, this is the code. Again, I'm not going through the details, but pay attention. Here is we're doing the Fourier transform in the MATLAB. And we can show the amplitude spectrum and the phase spectrum for the cosine signal. And we use 32 points to do the fast Fourier transform. Apparently that they are different from the spectrum for the ideal cosine function. The last example is how to demonstrate Gibbs phenomena. So Gibbs phenomena shows only at discontinuity points. So if we're trying to use limited number of harmonics to synthesize a periodic signal with discontinuity points, at this point we're going to see some overshots. And here is the fundamental frequency of the rectangle signal. Based on the Fourier series, we can figure out the spectrum for this given signal in the frequency domain. And we know that the original signal in the time domain can be represented using this infinite number of terms. But what if we have only limited number of harmonics? This is an approximation. When the capital N is an here is the approximation. When N is an finite number, then this signal is only an approximation of the original signal. And here is the MATLAB snippet given the number of harmonics, we can approximate the original signal using this equation. And here's how we implement it. And if we set capital N equal to 5, only 5 harmonics, here is the approximation of the original periodic rectangle signal. And here is when we increase capital N equal to 15. Now we see the wiggling is getting smaller, but the overshot, the amplitude of the overshot is the same as the N equal to 5 case. What if we increase the number of harmonics? We can see that the wiggling is getting smaller, but the overshot is there. And whatever you increase the capital N2, the wiggling is getting smaller and smaller, but the overshot is always here. So that is the demonstration for Gibbs phenomenon. Thank you.